Okay.
We're gonna start?
Yeah. Good morning, everyone. It's my pleasure to introduce Professor Chen Li from UC Irvine. So he's a professor in the Department of Computer Science there. He received his PhD in computer science from Stanford University in 2001, and his master and bachelor's degree from Tsinghua University in 1996 and 1994. His research interests are in the field of data management, including data cleaning, data integration, data-intensive computing, and text analytics. He was a recipient of the NSF Career Award, several Test of Time Publication Award, and many other grants and industry gifts. He was once a part-time visiting research scientist at Google. He founded a company called the Search2 to develop an open-source search engine with high performance and advanced feature from ground up using C++. Without further ado, let's welcome Professor Chen Li.
Thank you, Yunyou. I hope remote people can hear me well. Thanks for having me here. It's good to see many familiar faces, including one of my former students here. So the topic of the talk today is about something between text processing and database management. And the work, I want to say, is work in progress. And we've been working on this topic for the last 6 months, partially influenced by my interaction with Yunyou's team on System P. And I would love to take this chance to tell you what we have been doing, what our vision is, and I will also would like to get your feedback on the direction we're headed. Okay. The motivation is text. And we all know for this audience that text is everywhere. A large portion of the information we're dealing with is in the form of text. Now the main question is how to manage text, how to store the text, how to index the text, how to query text, and then how to do reasoning about text. Now, there are a lot of tools available on the market for text processing. At least some of them. Clearly, by no means this is a complete list of all the tools. First, databases. I mean, we have lots of experts in the database field. All the database systems, they do have some basic support of text processing. Like take MySQL or DB2 as one example. You can do keyword search using the right syntax. But for most very heavy traffic websites, they don't rely on a database to do very advanced text processing. Meaning because, from my perspective, text was not the main goal of database systems. Text is treated as a second-class citizen. And for most heavy traffic web servers, they tend to use like another middleware layer, like search engines like Lucene, Solr, and Elastic, to name a few, because this middleware layer is mainly designed for making text search much better. They build their own inverted index structure. They do their own advanced text processing, such as stemming, tokenization, stop words, and that is not the strength of a database system. Okay. In addition, there are also a lot of packages for natural language processing. Here I only list one of them, like Stanford NLP, but there are other tools available on the market. And then LinkPy is one more package for doing text processing. And then IBM here, you have a project on System P, and our work is partially motivated by your work as well. Okay. I need to get used to this little pointer. Okay. So what's our vision? The vision is based on my past experiences in research, also from the startup. I noticed that in many cases, text tends to be processed in a pipeline way. Okay, you have some original data. You want to do some operations. First, maybe put data either in files or inside the database system, and then on the data you can do some processing, say the keyword search or a reg expression, or you can use a dictionary to do some labeling to extract entities, or you can do more advanced machine learning or deep learning algorithms. Okay? And it tends to be processed in a pipeline fashion. But then very often, this pipeline tends to be very ad hoc. It tends to be written in some languages or such as Python, Java. In addition, a lot of processing, they do share some common operations, but those operations, they are implemented in an ad hoc way. And another problem is many of these operations, they cannot benefit from any available index structures. They tend to, if you had a data set of, say, 500 million documents, these operations tend to process those documents one by one. Using database terminology, we tend to use a scan-based approach. Okay? And this kind of approach is good because you can apply very advanced logic for each document. But the drawback is, if the data gets too big, then you need to do a lot of operations on your data, then you have to do it again and again. One example we have experienced was, say we do a regex. Okay, we do a regex expression one data set we're using, which is Magdalene publications, which has about 26 million abstracts. And based on our initial experiment, running that experiment on the entire collection of 26 million records will take possibly hours or even days. And that's not very acceptable for many applications. And plus, in some cases, you have one record expression, and suddenly, for some reason, you want to make a minor change to record expression based on the need, and then we need to run it the whole thing again. That's another maybe 1 day or 2 days. Or maybe your data has changed slightly by adding maybe 10,000 more documents. You might need to run the documents again, run regex again. Or if you have a dictionary of the city names or company names, you already run some operation on your documents, and for some reason you added maybe 5 more cities, or you deleted some of the cities, then you have to run the whole thing again. So this kind of repetitive operations are very time consuming. It'd be really nice if this processing can benefit from availability of some index structures. Okay? So based on all these observations I've seen, we have our vision of the following, which is we want to build a text-centric data management system where text is treated as a first-class citizen. So this one is designed just for text. Of course, we all know for system people, when you build a real system, even though at a high level it's all database system, but for different purposes, for different types of data, different applications, at a very low level, you make many different decisions. And take databases for example, that's not the main focus of database systems. But for the system we want to build, we want to treat text as a first-class citizen. We want to provide some primitive support for some of the most widely used operations. We want to put them, making them available from the system.
So do you intend to make it both text-centric and data-centric, or is it really a text management system and not a database system?
The question is really about whether it's text-centric or data-centric.
I'm wondering if it should be and would mean they're both first-class citizens.
For us, our decision is mainly on text. I view text as one of the kind of data. So it's just text. And I think when I go through some of the basic operation we already support, maybe the question will become more clear.
So why not call it a text management system?
We could. I'm not very religious about the name.
Okay.
Okay, this is just one template for now. So one thing is we want to make it possible for applications to put your data into the system. Then you can treat it more like a storage layer. You don't need to worry about storage, indexing, that kind of low-level details. And plus, this system can provide you some basic primitives that are commonly used by many applications. And then you don't need to worry about how to implement another very efficient regex expression evaluator, or entity matching or other operations, or even for some more advanced operations like NLP. So those primitives will be available to applications. And one more thing we want to do is, for some of those operations, if they are indexable, they can be used by available, say, inverted index, then we would like to see if for that query we can avoid a scan-based plan, and that can speed up your app development much faster. So these are the few goals we want to achieve.
Yeah, so this is the focus is mostly on the query and search part. But what about the curation part?
Search is one of it, and I think maybe I can tell you what we have done so far, and then what we have not done yet.
Yeah,
That
but there is also the curation part.
Right,
This
yeah.
is in the curation, or that's a separate?
We have not done that part yet.
Okay.
I think it could be on our roadmap here. So, in addition, our vision is we would like to borrow what we have done in the database community, which is we can provide a declarative language for the programmers to say what they want. And this has not been done yet, but this is our goal. At the same time, I want to make it very clear that this is not a system that does everything. Okay? That would be stupid to make that position, because we know text processing is very complicated, and there are many other things that's not our role to play. And the role we play in the whole ecosystem is, if we have this ecosystem of multiple steps of text processing, we would like to play the role of the first step, where you can put it there, you can just don't worry about the loss of data, and in addition, you can use this layer to do some very basic primitives very efficiently. And once you get data, you can do whatever you want to do based on your logic. And this is the role we want to play in the ecosystem. So a few requirements. The first requirement, based on our database experience, is we want to make it declarative. We want to make it composable using basic building blocks. Here we use operators. So we want to model all those operations as basic operators with the same interface. Then we can combine the different small building blocks to come up with a more complex, fancy, and more expressive query plan. Okay? The second one is it has to be efficient. If your query processing could benefit from available index structures and algorithms, we want to do it. Okay? And one of the examples we show is regex. How can we make regex indexable and more efficient? Okay. So this is the architecture of our system we have been developing. We call it TextB. From name, you can see what we are after. At the bottom layer, we decided to choose Luxin, and I'm going to explain why we make that decision. This is a decision we made after a long thinking process. We use Luxin because Luxin has many good things I'll talk about later. And on top of this storage layer, we build some basic primitives or operators. Currently, we already supported 3 operators. I'm going to explain them one by one. Keyword search, dictionary match, a few other operators. And then we have, on top of it, we can use the basic operators to compose more complicated plans by combining the basic operators. And the one in the red dotted box is not something that we have not done yet, which is, well, after we finish this one, make it reliable and efficient, we would like to have a language layer that is declarative, and then that clearly the query needs to be compiled and be optimized and translated into some physical plan that consists of these basic operators. Okay. And then here, for those applications, we put the system T as an example because, as mentioned earlier, for some operations system T is doing, we'd like to see whether this system can benefit your operations by making some operations indexable and more efficient. Okay. And when we made these decisions, we thought about a lot because we were building a system, and the context is for people who know me, we have done lots of work in the space of data management. We know how the data engine is designed and the pros and cons of a database system. And here we largely borrow idea from the database community where operators are the basic building blocks, and they can be used to combine to form more complicated plans. Yeah, the other one decision we have made is Luxin. The reason we use Luxin, the simple answer is we can stand on the shoulders of the giants, and we could start from scratch to build a storage layer, because we did it before in a few other systems. But at the same time, based on my personal experience, I felt that building a database storage engine from scratch could be very, very challenging, especially when you deal with incremental updates, concurrence control, all those issues. It takes lots of time to make sure the system is efficient and reliable. At the same time, Luxin has been proven to be the leading solution in this space, and it's very, very performant. In addition, it has very rich set of analyzers and query support, and internally it has pretty powerful inverted index structure to support many operations. And some of the operations we would like to support, we were able to convert those queries into some queries on top of Lucene. So these are the benefits we can get by using Lucene engine. Okay. Now we didn't use the Solar A layer because we want to treat it as a library currently. Solar is a separate web server layer that we do not want on the bottom. And forget about the Elasticsearch.
I don't know much at all about Lucene. Like, what is this normal environment? What do people use it for?
Many people use it for search. I think even for IBM, at IBM, the field project using Lucene. IBM. Also, I think IBM is one of the big supporters of Lucene.
Yeah.
Lucene, Elasticsearch,
Yes,
Solar.
correct. And I think
IBM Cloud, actually, yeah.
IBM also invested tremendously in Elastic.
Yeah.
Elastic is more on the parallel setting where you have a cluster of machines, right?
Yeah.
But for us, since we're building the engine bottom up, we choose this library layer, not the Solar layer, not the Elasticsearch layer. So we start from there. And since for this text domain, most operations do not require a join operation between multiple documents. I believe for large data sets, it can be easily partitioned into multiple machines. We can easily build a separate layer to make it scale. So that's why we picked the Lucene library. At the same time, we have some benefits. We also need to live with the limitations of Lucene. And in fact, for some of the operators we try to implement, we encounter some barriers whether Lucene can support it. The good thing about Lucene is it's very powerful. At the same time, it's very encapsulated. And it's not easy for you to get into the library to make some low-level changes. And plus, you don't want to make low-level changes because it had to be very compatible with the future releases. So we have to treat it as a library, but also we have to live with the current limitations. I'm going to talk a few places where we already encountered the limitations of Lucene. Okay. Now, our vision is general about text processing, but at the same time, given our initial stage, we want to stay focused. We want to just focus on information extraction. And plus, information extraction itself, I believe, is already a very big market. And if we can succeed in the direction, we already have kind of impact. Okay. So this is an overview of the rest of the talk. I'm going to first talk about a few operators we already implemented. And then we talk about the one particular one, which is regex, which is pretty interesting to look at the details. And we talk about some initial form of numbers, and then we talk about our future open challenges we're facing. Operators, I think most people in this audience know. We borrow the same idea from database systems. So each operator is supposed to implement these three functions. Open, where you do the initialization, resource allocation. And then you get next tuple, then the caller of this operator can keep calling this operator to generate, to suck all the results from the operator. And this operator can implement its own get next tuple by talking to its children, which also provides those same interfaces. And then at the end, you do the close and you release all the resources. And we want to use the same idea for managing text. Now, this is a list of operators we have already implemented in the last 5 months. I'm going through some of them, and there's some other operators are still on the roadmap, and I would love to get some feedback about some other operators you would like to include on this roadmap. Okay. The first one is keyword matcher. It's very natural because of text, keyword search might be the most natural way to get information out of your text. And here, the idea is, one example is I want to get all the documents mentioned in Zika, Olympics, and Rio. Right? And here, I give you a string, and we want a system to find those documents mentioning those three keywords. So when we design this operator, currently we support 3 different kinds of semantics. The first one is just a very simple conjunctive query. I just use analyzer or tokenizer to divide to tokenize your string to multiple tokens, and then I treat it as a conjunctive query, ignoring any position information. Here, Lucene has a very rich set of analyzers based on your language, based on your need. And here we use the default or most popular one, which is called a standard analyzer, which is very common for English language.
So is the answer to a query going to be a set or a sorted list?
The answer to the operator is really is a set. Using a database
So there's no,
semantics.
this one's better than that, just every single one that has
Correct.
that word
There's
in
no
it,
order
No
here.
matter how many times the word appears, no matter what, just boom, they're all there.
Yeah, so here it's using this database concept. There's no ranking, and there's no order, and the operator does not guarantee in which order the results are returned. Okay, very similar to operator works in database system. Okay, so that's a very simple interpretation. In addition, we also support two other semantics. The one is phrase matching. Phrase matching means a good example is New York, right? The user types in New York, and I want to treat New York as one phrase, and New and York should appear together in your documents, right? Other examples is like Hewlett Packard or Barnes and Noble. This kind of named entities want to treat as a phrase, and Lucene supports phrase search, so we want to provide this semantics to the user. The third case is really a substring. They give you a whole string. I just treat it as a raw text of substring. I want to find all documents that match this one as a substring. Okay, and for these three semantics, the first two are indexable because they can be based on these tokens, and tokens can be queried from the invert index. The third one we just do a scan. Some of the operations cannot utilize the invert index structure. Okay.
So the real difference then is that in the case of substring, it could start from the middle of a word.
Correct. The question is whether the substring can start from the middle of a word. The answer is yes. I mean,
and that is what distinguishes it from phrase, right?
correct.
Phrase
Phrase
consists of full words
yes.
that
Yeah.
are contiguous.
Yeah. Phrase has this meaning of word boundaries.
Yes. That's what-
Substring doesn't have it. A good example is rain, where we match train. Right? Rain is starting from the second letter of train. So as substring matching, rain will find the train. Okay.
Even space in the middle of the substring, so it has the last half of this word plus a space plus the first half of the next word.
Are you talking about substring or phrase search?
Substring.
Substring can match the suffix of a previous word and the suffix of next word. That is possible because that
And
is
the
substring.
prefixes, It needs
Yes.
to be consecutive thing,
It's
putting a
consecutive.
space in the middle.
It's just a substring, and they treat space in the
It's
same
just
way
another
as other
character.
characters. There's no special meaning for space.
Right.
Okay, and if your application needs this semantics, we give it to you.
Right.
Okay, and you could do something fancier by analyzing the space in the query to make it indexable, but then we're entering one territory where the meaning of a word becomes very vague. So we didn't take that approach. That's why for text, language processing becomes very important. What's the meaning of a word? I mean, even for other languages like Chinese, Japanese, these two languages, detecting the word boundaries is a very big deal compared to Latin languages. Korean is different. Korean is kind of a Latin language.
So that brings up the question of, so you're not doing n-gram indexing to, even for substring matching, make it more efficient?
Oh, okay. The question is whether we can use n-gram indexing for substring matching. I mean, that's a very good question. Currently, we don't do it. But in fact, it's doable. Right? You can generate multiple grams and use a gram invert index to do it. In fact, that's a good idea. In a different system, we do it. Okay. But we can make it work in that direction.
So how do you really discover the phrases? Are you using machine learning to do that?
Oh, the question was where we get the phrases. The short answer is it's a job of the programmer. Right? That's not our job. Right? Because as I said before, I want to make my role very clear in this ecosystem. Right?
So somebody mean outside it, feeding it through a dictionary.
Somebody means the user of the system. The user must have given us the phrase. How the phrase was formed, that could be done by a different task. Currently, that's not a focus of this operator. This operator assumes.
Yeah, but this operator has to also recognize the phrase in order to find it in the index. So there should be some sort of dictionary that you should be using.
But for this operator, we assume the user gives me one phrase, and we apply.
But the query has, words, but you have to discover there's a phrase in it.
But the user would tell me I'm using a phrase operator. I mean, it has to be very
But in
explicit.
search typically they don't do that. But first you discover phrases typically nowadays through machine learning.
Right.
But because there is no dictionary out there, you have to discover that dictionary. But when the query comes in, the user doesn't put like double quote around the phrase. It just gives the phrase, so you have to match the sequence of words in the dictionary to figure out, oh, this is actually a phrase.
Yeah. So for remove people, the question really about who gives us the phrase. Again, our answer is this is the decision made by the user.
So
Yeah,
the user has to put a double quote around it.
You talk about the syntax. Yes, since our current text space is running as a library, we give you some example later to see by passing one parameter, the user is telling the system treat it as a phrase. Okay. Where the phrase comes from, that's not the system job. Okay. And that's why I said we're not solving all the problems. So this is the one example of how we use this keyword matcher operator. Again, the text space is currently running as a library in Java. Here you can just say new keyword matcher, and we give a predicate. When you define the predicate, you can say I use a conjunction index space. The meaning of this word means treat this string as a conjunctive query, and then you can use the index space approach. Okay. This is the meaning of that flag. And you can also say I can replace it by phrase index space. And to answer your question, if the user passes this flag, it says I want to treat it as a phrase and do index-based search. The third one is substring matching here. So it's very declarative. Okay. I mean, not in the language phase, but at the library, from a library's perspective. Now, internally, how we do it inside Lucene. I want to use this example to show you how we translate some operation of our library to something internal. Internally, since we use Lucene, what we do is really generate Lucene query. Okay. Again, you don't need to go through detail. The main idea is if you give me one string, I do the tokenization using the standard analyzer, generate all the terms, and I construct this Lucene query using their library calls. And I pass the generated Lucene query to Lucene. Lucene will run the query and give me the result, and I'm going to consume the results using the get next tuple interface. Okay, this is the internal translation. Okay.
So you're only using Lucene. There's no like knowledge graph or metadata that you collected from the thing to match this thing.
So the question is whether we're using Lucene. The answer is yes. Currently, yes. Because for now, the current focus is how to make those operators implemented and make them efficient. And I mean, our roadmap is very simple. Let's first make this one work, complete, stable, and then based on the needs from applications, we can add more features. So they can be done in the future.
Yeah, because typically you get the metadata in some JSON form. But if I look at it from the database viewpoint, it's a combination of JSON query processing and indexing and Lucene, not just Lucene. Because Lucene really doesn't understand JSON very well.
Yeah, so we are now doing many other fancy things. For now, our position is very simple. We use Lucene to implement those operators, and they say how to make them happen, and how to make them efficient. And there are many other things we can do in the future.
Yeah, I mean the problem is once you get to knowledge graph, I mean Lucene is just an index, but knowledge graph is far bigger than Lucene.
Yeah, so that's why I said earlier, we're now using this system to solve all the problems.
Okay,
We only solve the basic primitives. The second operator we have implemented is a dictionary matcher. A good use case is if you have a list of drug names or disease names or city names or company names, you want to use your knowledge to do some marking in your documents. So that's Microsoft, this is IBM, that's Google. So this is one easy way to use your a priori knowledge to do some information extraction. So the way we model it is you have a collection of documents, you have a dictionary of entities, and you want to use these entities to do the labeling or matching within your documents. Okay, and currently what we do is we just use the basic keyword matcher. Very simple. I just go through the entities in your dictionary one by one, and for each of them, I just call the corresponding keyword matcher to do the matching of the documents. Now, here, since we have 3 different ways to do keyword matcher, we have the 3 corresponding ways to do the matching for dictionary. Now,
So what's the overall idea behind what this operator is doing?
Let me repeat. Let's say I have a list of company names, and IBM Microsoft, and I have lots of documents.
Or you want to find all
I
the
want to
matching?
find those places that are companies. Okay, this is the purpose of the operator. because this is the knowledge I already have. You don't need to rely on some more advanced algorithms. This is the basic knowledge you have. You want to use a very simple way to do the markups of this.
So what you're trying to do is in one pass try to deal with many queries effectively.
There are different ways to do the evaluation. And this come out of a joint to some degree, right? We have one dictionary of entities, one collection of documents. We want to do join, where the join is a substring matching here. You can view it that way. So the current implementation we have is I scan the entities of the dictionary one by one. For each of them, I call the corresponding keyword match operator. It's more like an index-based scan join. You can view it that way. Now, other things we can do better. For instance, if your document collection is not too big, but your dictionary is huge, and this one, the outer relation becomes too big, this one becomes too small, you can reverse the order. You can even build an inverted index on your dictionary. Right? This is very similar to what we do inside database system. Okay. In our first implementation, we just do a very simple index-based nested loop join. Okay. This is the room for future optimization.
Is this more efficient than actually getting all of it from using? I'm not very familiar, but to actually get the results for each keyword out of using and then merge it, is that more? I presume it will be less efficient.
The question is whether it is more efficient to give everything to Luxin, right, rather than doing the one by one. Luxin, we didn't try it, but Luxin has certain limitations. If I have a dictionary of, say, 5,000 companies, you could have more like a disjunction of 5,000 entities. But I don't know how well Luxin can handle that kind of a very big fat query. I don't know. And I feel even Luxin internally let me do something very similar. So we didn't try that path, but we can do some experiments and see how it performs.
So what's the user's expectation? Is it a union of all the documents that match those dictionary terms? Or for each term you want to explicitly give which are the matching?
Okay, the question is about what is the output of this operator. Okay, when we design the operator, we use the same idea inside the database system, which is the output of each operator is also a stream of tuples. Okay, in this particular case, if I have IBM, Microsoft, or Google, these three entities, and then for IBM, if in my documents I have 10 records mentioning IBM, and for each record, even if IBM appears multiple times, I'm going to return that record as one tuple.
Yeah, that I figured, but right. If the same document matches IBM as well as Microsoft, is it going to be returned once or?
It's going to be returned twice. Because we assume every occurrence of one entity, possible multiple occurrences in one document, is treated as one tuple with multiple spans.
So the output's a multi-set, not a set? And the document can appear twice in this set?
Well, each tuple returned from the operator is all the occurrences of one entity in one document. Now, if IBM appears 2 times in document number 3, that information is returned as one record. If Facebook also appears once in this document, that information will be returned as another tuple record. You can say more like every pair of entity and document is returned as one tuple. And if one entity appears multiple times within one document, then that multiple occurrences will be encapsulated as a list of spans. We had a discussion about whether we should return the spans one by one or a list of spans, and we decided to take this way mainly because I think from the application's perspective, it's more intuitive to deal with one document in one batch rather than getting the multiple spans one by one. I think that's easier for the programmer to write their own.
So it's more efficient, right? You can
yes, we can reduce number of function calls between the next layer and this layer. So this is a decision we made. Okay. Fuzzy token manager. I think this one example is I have Zika Olympics real games disease virus. I want to look for all the documents mentioning these few keywords, but not necessarily all of them. Maybe 4 out of 6 or 3 out of 6. And this kind of operations for people who work in this field, you should know, is very important for many cases like entity matching, schema mapping, even keyword search. In keyword search, my classic example is like our former governor, Arnold Schwarzenegger, right? And everybody knows he's popular as a star, as a politician. But few people know how to spell his last name. Right? So try it without using Google or any other search engine, see if you can succeed. So these kind of cases can happen where you're looking for some information, but you don't know exact spelling of the word. But in general, you look for something, but your matching condition is not exact. Okay, so the timing is interesting. I just used this example that happened just 2 days ago. Right? For this case, I hope nobody get offended by this example. So in this example, we have two speeches, and it's a good example of similarity search. If the speechwriter had a chance to run some operator to see if part of that Mrs. Trump's speech can match any of the earlier speeches, that kind of embarrassment could have been avoided. Right? So this is the detailed comparison between these two speeches. So this is the way the user can use this fuzzy match operator. It's just a fuzzy match operator. You give the predicate inside the predicate, you give all information. This one we are using currently. We're using the Jacquard similarity, or no, the number of common tokens. This is the way we define it. Even though there are other ways you can define similarity. And so when we implemented this operator, we are facing the issue of whether Luxin can do what we wanted. Because for people in this field, there are a lot of algorithms that have been developed in the literature about how to make similarity search really efficient, including some of the work my team did in the past. And we have some very nice algorithm to make it fast. The question is whether we could use the existing Luxin's API to implement that. This is the problem we were facing. And we did some analysis and found out that Luxin is not easily hackable. So some of our early algorithms cannot be easily implemented using the Luxin's current infrastructure. But the good news is Luxin already has a nice feature where you can say, when you do the match, you can say how many tokens, what's the minimum number of tokens must appear in your documents. We can just benefit from this one here. And it'd be interesting to know if we were to implement some of our early algorithms and do a comparison of performance, which one is better. But for now, this one is doing what we're doing here. So we're pretty happy with this limitation, with this feature. Stanford NLP operator, and for people who don't know what it is a Java package that can do natural language processing. Okay. And we implement this whole thing as one operator for two purposes. The first purpose is we want to see if TextDB can really provide some basic natural language processing operation as operator. Okay, this is one purpose. Second purpose is we want to use Stanford NLP as a guinea pig, because there are many other open source packages available there. Most of them written in Java, Weka, other libraries. We want to see how likely it is to integrate these open source libraries into this framework as operators. Okay, if we can succeed in this operator, this package, then we are getting more confident that we can also include other packages into our framework, as long as the license agreement is good. Okay, and we succeeded in this experiment. So here, we know this is what the Stanford NLP package can do. You do very advanced analysis of your text document. And what we did initially is, by using this package, we're able to do two kinds of entity recognition. One is named entities, classes, like numbers, locations, money, persons, dates, and times. And this is what the package can provide. The other kind is part of speech, like adjectives, adverbs, nouns, and verbs. And these two kinds of entities are already supported. Now, natural question is, if you use this package, the good thing is this package is very sophisticated, very powerful. Okay, we can do many fancy things. Internally, you can imagine this library has its own lexicons, other knowledge to see this is a company name, that location. The good thing is it's very powerful, and the bad thing is the performance may suffer, because this approach will scan your document one by one. And I think many people told me Stanford NLP is very powerful, but one of the challenges is low performance. Okay. But we want to include this one into this framework, and we did it. This one is an easy one, which is give a query with some typos, I want to fix it. This one has nothing to do with the machine. And this exercise is to show whether you can implement some more advanced operation as one operator. Here, if you miss the space between Olympics and Rio, by running this operator, you can fix it. You can get the one with the space. Okay. This one does not rely on machine. So those are basic operators. And I want to pick the next operator, regex, and go through some of the details. How are we doing in terms of time? Okay, 43. All right, so next I want to dive into the details of one operator, regex, because this is something that technically much more challenging than all the other operators. And it's also one of the most commonly used ways to process data, and scalability is a big issue. Okay, and we decided to implement this one in the system by using an index-based structure, using inverted index. Okay. The algorithm we implemented is coming from engineer Ross Cox. The background is he, about 10 years ago, he was working on this Google Code project. He wanted to support regex search on Google Code. So he modified one of the early algorithms and proposed this algorithm. And then this algorithm was indeed deployed in a Google search service. Later was terminated. But the code is available in Go, the Go language. The idea is the following. You give me one regex, okay, like I'll talk about some examples later. It's going to generate a corresponding Boolean expression, Boolean query using grams. And this Boolean expression based on grams is pushed to the engine to run and give the result, which can have false positives, and do the post-processing by running your automaton on those candidates.
False positives?
Because this one, the way to do translation can give you a necessary condition, not a sufficient condition. So it could give you some result that don't meet your regular expression. So you need to post-process. You need a very efficient evaluator of regex expression. Okay. So the example is for that regex expression, by going through the translator, we generate this Boolean expression with it's a conjunction of it's a disjunction of conjunctions. Okay. And then this Boolean query is pushed to this Luxin engine, which internally has an inverted index, and that query is evaluated to give you candidate documents, and for every document you run it through your automaton and do the final verification. So
what kind of regex does they support? Because what you are showing here, for example, other
yes,
/d, /w.
Yes, the Yang's question was what kind of regex expression we're supporting. I didn't include a slide here. So regex, first of all, based on our knowledge, there's no common standard. Different libraries, different platforms have different syntaxes. In addition, we start with these 5 basic operations, expressions, and there's more other expressions. And this algorithm may not work for some of the expressions. It covers most of the cases. We can talk about those cases that cannot be covered by this algorithm. But this is a simple for this audience. So these are the 5 basic operations to define the expressions in a recursive way. And then one thing, very important function is if you give me a string, how to generate a Boolean expression of grams. If the string is very simple, no fancy expressions. So here, the algorithm works for our implementation allows you to use any gram, like trigrams, bigrams, or 4 grams. But for us, it's just a parameter you can pass to the engine. Okay. The original algorithm assumes it is using 3 grams. So for the rest of the talk, I'm using 3 grams, even though you can change 3 to 2 or 4 if you want. Okay. So if we use 3 grams, if the user is giving us AB, then since all the grams are these 3 characters, then sorry, you cannot use this invert index. So any means you have to process everything. Okay. Now, if the query string is ABCD, then when you generate the grams, you have 2, 3 grams. ABC, ABCD, and it's a conjunction of these 2 grams.
So, in the case of AB, you can't do prefix search on the trigram?
In the case of AB, if you use the inverted index, you cannot do it because inverted index, the basic units are 3 grams. And we are not assuming any trie structure here. If you had a trie structure, you start using a trie to see, starting with AB, you can have a lot of completions, and each of them can have a big disjunction of this 3 grams. But we're not doing that calculation because, I mean, there'll be too many expansions. AB can generate too many trigrams. So it's a trade-off here. So this decision we made is you just scan everything. It depends on your alphabet, your vocabulary. The alphabet. If alphabet is small.
What I thought was you just go into, I mean, it's like any other B plus tree index, right?
Right.
You can always go in with the prefix of the key.
Correct.
And it's not like you are explicitly completing it. The index itself just.
Yeah, I mean, the question is for this kind of AB prefix, whether we can use index structure to complete it.
But I'm saying they will all be contiguous anyway.
Yeah, but the issue here is if we had a structure started from scratch, we have more control. But for our case, since we use Lucene doesn't expose that API.
Oh, I see.
Right? In a different setting, we did a try, we did a completion logic, but we didn't do it here. Right? And plus, in terms of performance, I doubt if that completion-based approach will be efficient, because for the English language, AB will have a lot of completions. You have a huge disjunction of a lot of trigrams. It might not be very efficient. You might better just do a scan. We know in database systems, if you touch so many records, it might be better just to scan everything in terms of disk I/O performance. Now, if you have a set of grams, ABCD and WXYZ, set means is a disjunction. Then you generate a disjunction of conjunctions. Now, next few slides, I'm going to use one example to show the main idea of the algorithm. A lot of details I will not cover, but I think that's good for this purpose. So in this example, I have this reg expression DATA star. Then keep in mind the star is on A, is not on data. So that means DAT followed by any number of A's, including no A, and then followed by a disjunction of BCD or a PQR. So this is the meaning of reg expression. Okay. So give this regex expression, we first do the parsing, and we generate a parse tree. So we have 3 different kinds of nodes, like a concatenation, it's more like a followed by logic, and then the leaf nodes are all literals, which are basic strings. We have DAT A, the modifier is a star, means 0 or any number. Okay. And then the BCD and PQR, we do a disjunction, which is alternation, between two strings. Let's see how the algorithm works on this reg expression. The main idea of the algorithm is for first reg expression is defined recursively, right? The expression is defined using other expressions until we reach the bottom, which has all those strings, literals. So for every expression in this tree, the algorithm maintains some variables to keep track of some information. Okay. The most important variable is a match, which is essentially the corresponding Boolean expression using trigrams. Okay. This is the kind of the placeholder for the final expression. And then in addition, it keeps track of 3 variables: exact, prefix, suffix. And from the name you can tell these variables are keeping track of the kind of necessary conditions, meaning for a string to match that particular reg expression, what suffix that string should have, or maybe set of suffixes the string should match. What set of prefixes the string has to match, or what set of exact strings this one has to match. So these are the 3 conditions, and these 3 conditions will be appended to your match expression to make your condition tighter and more efficient. Okay, so and then this is the purpose of those three variables. And then when we do some reasoning, when we combine the expressions from the next expression, we need this variable called empty-able as a helper. Empty-able, from the name you can tell, indicates whether matching string for that regular expression could be empty string. And this variable will be used when we recursively compute all those variables from the next layer, from the bottom layers. Okay. So here, this is a parse tree, and let's start from the DAT. So DAT, it is literal, that's not empty, so we know it is not empty-able. Okay. So the empty-able is false, and then exact match is that DAT prefix, suffix, they're all DAT. This is an easy case. Okay. The corresponding match, you call the trigrams function. You get the simplest Boolean expression using grams. Okay. That's the starting point. So then you go to this literal with a subtree here. So empty-able, it becomes true because A star could match the empty string. And exact, we don't know what exact string is. It's unknown. And prefix is empty. Suffix is empty. And match, you can match anything. So now we have the information about these two subtrees. And then when we look at this, since when we do the evaluation of this parse tree, we do this thing is a kind of a left associative. Okay, so we first look at these two subtrees and do the concatenation, which is kind of a conjunction. Okay, and then what the algorithm does, it would take a look at these two columns, and then based on certain rules, it will calculate the variables for the third column. Okay, example is the empty-able case. If the first one is false, the second one is true, we do a conjunction because the top level is concatenation, which is a conjunction. So the empty-able is a conjunction of these two empty-ables. Okay, so it becomes false, and there's some other rules you can follow and match. I mean, so by following the rules, you can calculate these variables for this new concatenation of the two subtrees. Okay, and then do the same thing for this tree, which is a disjunction, because BCD or PQR, it is disjunction. And then you combine this whole thing, and finally you have this 5 variables for the whole tree. And then the last match variable is the final Boolean expression using grams. Okay, so here if you draw this way, if you draw the Boolean expression in the tree representation, so it's going to be these 3 things, these 4 things. You do the conjunction, and then you do a disjunction of these 4 children, and do a conjunction with the DAT. Okay. And then after this step, we need to use the 3 variables: prefix, suffix, and exact. So these 3 variables will be generating some additional conditions to your Boolean expression to make it tighter, because you want to make your query very efficient. Okay? So you put this additional information from the 3 variables into your Boolean expression tree, and that will be the expression you can get. Okay? So once you have the expression, you go through a step of simplification logic. So here we generate, we convert the whole thing into a disjunctive normal form by pushing this conjunct of the conjunction into this piece, and then after you have this Boolean expression, you can apply some other simplification rules. Okay, one of the rules is if A or A and B is equal to A, meaning you can remove B because you have A outside. Okay, you apply this kind of rules on this expression tree, and this is a simplified final Boolean expression.
But the middle part will still be done as a residual predicate, right? The A star.
A star. A star.
In the original expression, you have the A star in the middle.
Yes.
That would have to be done as a residual for the same reason we discussed before.
But in the
trigram cannot be used.
Correct. In the process, the algorithm does make some steps to get rid of some of them. So it is possible. So the algorithm has to make some trade-off by getting rid of some of the conditions.
Because I noticed you had some APQ and APC and things like that, right?
The ABQ, which one here?
The last slide you showed had some of those. Yeah, I mean, there you see ATB.
ATB, this one comes from here. This comes from over here. So I didn't explain how this one generated. It's a concatenation of the suffix of the left one and the exact of the right one. But to get the exact one, you get a suffix one, you concatenate them. That's going to be your suffix, new suffix. That's why it's getting longer.
Oh, I see. Coming from the initial BAT.
Yes.
Not from the middle A star.
Yes, yes. It's not the A star. I think in this example, might be ignored at the end. It doesn't give you any pruning power. So in the details of the algorithm, it makes some certain decisions about getting rid of some of the conditions, because those conditions, if you treat them very literally, they can give you too many conditions, and that can make your query too big. So that's why this algorithm has a lot of room to be improved. So this is a finally simplified Kleene expression. Now we can go through some other expressions, see how it works, but the main idea is here. Okay. So next I'm going to show you some of the initial perform numbers, and also I want to repeat the fact that these are some initial numbers. We have not done a very deep profiling of where the bottlenecks are. Okay. So the data set that we use is, I mentioned earlier, is a medical publications. We mainly focus on the abstracts. This is from Medline. We have a collection of 26 million records. Okay, and the abstract is the longest attribute in the schema. Setting, we didn't use a server. We have the story is we have a whole bunch of students working with me for the last few months, and we just use one Mac. And the main message is really about the trend. So don't take the absolute numbers too literally. First of all, we have to compare this approach with like System T approach, where you do a scan. For that kind of approaches, you don't pay any overhead of the offline indexing phase. So for us, we had to pay the cost. Similarly, inside database systems, we have to pay the cost of creating indexes. Here we care about two things. One is the time to build the index. The other one is the index size itself. We tried the different sizes. And the time, you can see it grows linearly. This is the behavior of Lucene. It's not our credit. We just want to see if encapsulate Lucene to do these kind of operations, how this Lucene engine works. So the whole thing grows linearly. Not too bad for like 1 million records. It takes about 5 to 6 minutes to build an index with about 22.5 gigabytes of index structure. Okay. But when we build this index, I want to emphasize one thing, which is since Lucene heavily relies on the inverted index, Lucene allows you to build different inverted indexes using different analyzers. And depending on your semantics, what do you want to do with your data? And this is the result of using a standard analyzer, mainly for English. But when we do the regular expression evaluation, we have to rely on the inverted index of grams. Okay? That's a different analyzer. So that means if you want to support both queries, you have to build two indexes, one for a standard analyzer, one for gram analyzer. So it's similar to what we do inside database systems. One index is for one purpose. And if we make the whole thing declarative, we can say what kind of indexes we want to build. Okay? So, and when we do the trigram analyzer, this is the numbers. And the numbers, I think I'll leave it higher. You can look here, the 340, this is 1 to 1300. And the reason is simple, because when you do standard analyzer, you generate fewer tokens. When you do gram analyzer, you have more grams to generate. So your tokens are getting more, but your inverted index is getting bigger. So this is the cost you have to pay.
You should be able to use the trigram index for the standard one, right?
I don't think we can use the gram inverted index for standard analyzer, because a good example is there's a semantics inside it. Because if you use, say, New York, take New York as one example, right? if New York, if we use a gram analyzer, we generate a invert index with a new NEW, EW space, the W space Y. Right? This is our grams. Now, when you do the standard analyzer, it should generate new and York two words. Now, if a query comes in,
Yeah, but I still use the trigram and then do res,
yeah, I think the performance
ultimately-
may suck. The performance may suck.
And
Yeah.
also the standard analyzer also do a bunch of other things. I think it's turned into lowercase. It
Yes.
also do stemming.
Yeah, it becomes semantically richer. What do you want to do? And even if you could translate your standardizer operation into grams, I mean, you could miss some information, or the performance would be there.
Lotus Notes always used bigram for Eastern Asian languages and trigram for the Western languages.
But then one clarification: when you say trigrams or bigrams, I talk about the character grams or
Yeah,
token
yeah.
grams.
Yeah.
Character grams. Okay. But I want to know how they do it. How they use that character grams to do, like in New York. I would love to see how they do it.
I don't know if there's any paper that describes it, but that's what they did.
Okay. So talk about the keyword matcher. The keyword matcher, we randomly pick some of the keywords from the documents, and then we run this keyword query using our invert index, using Lushin's invert index, using our operator, which internally uses Lushin's invert index. So this is a curve to show how the number changes given the size of the data. I showed these numbers might not be final, okay? Because if see this is 100K all the way to 1 million, and the y-axis is in seconds. To me, these numbers are high, because I know Lushin is very good at returning results in milliseconds. But here we're talking about seconds. So our students are still doing some analysis. My theory here is the whole pipeline has two main steps. One step is running Lushin to get the results. That's one step. The other step is we go through these results one by one to do some post-processing. And I think in the current way we collect these numbers, most of the time is spent in the post-processing step, which could be easily reduced by doing some optimization. So I think a better way to plot these numbers is to separate the time into two pieces: Lushin time and post-processing time. I think these numbers mainly include the bottleneck is the post-processing time, which could be very very expensive. Phrasers, similar trend. Fuzzy token matcher. Want to see if the Lushin's this feature is very efficient, and the final results are pretty good. So we use different thresholds. Intuitively, the larger threshold is the tighter conditioning. If the threshold becomes 1, that means these results they have to match exactly. Okay? Because this is a similarity. 1 means a perfect match. So if we increase the threshold, then the number of results over multiple queries will reduce, and then the time will also reduce. So it means Lushin is doing a pretty good job answering similarity queries. Stanford NLP. Stanford NLP, if this is the input, and those red boxes will be the output. You can see that we have time and organizations and the locations. This will be output of the operator or the analyzer, and the results are not surprising, which is Stanford NLP package kind of slow. Okay, so for instance, when we use the whole time grows linearly. For 5,000 records, it took when we tried to get all entities, it took 320. You do the math, so it means 5. So each 1,000 takes 60 seconds, right? Each 1,000 takes 60 seconds. That means each document takes about 60 milliseconds. So that's the Stanford analyzer's behavior. And it'd be really nice to see if even that one can be indexable. But I think that's pretty hard, because they have some very sophisticated language model to process documents. But this is the way it is. This one we use a different computer. Regex. So this is a case that is kind of still pretty open-ended. We have good news and bad news. And the bad news is some of the common regular expressions, this algorithm doesn't work. That's kind of very sad. Like email addresses, for telephone numbers, the current algorithm doesn't work. But it also gives us the opportunity to do something better.
What does it work mean?
That doesn't work.
Meaning give wrong answers?
It would become a scam. You cannot utilize
it's
the
inefficient. Doesn't work means it's inefficient.
Yes.
Yeah,
So,
because program based on the alphabets.
yeah, I mean, when I say by works, I mean it'd be really nice to have an inverted index to get the candidates.
Yeah, there's some existing work on creating index for like Java type of the regular expression.
Yes.
But
Yeah, and some of the common expressions, they're not indexable. Maybe to be more precise, they're not indexable. But we have some ideas about how to make them indexable. But that's our kind of future work. In addition, it could be very controversial to come up with some meaningful regular expressions. And this is some expressions our students came up with. I just don't take them very literally. So for these expressions, the reason we put system T here, first want to make sure that the comparison is fair. I mean, these two approaches are very different. One is index-based, one is the scan-based. The purpose really is to show if we were to use this text to be as a preprocessor, how many candidates we can prune. So then later you don't need to do many things. Our observation is for some of the queries we were able to reduce the number of candidates to only 10% of the original data set. Right? 10% means you reduce the time to about 10%. Okay? It depends on the regular expression. And it heavily depends on how complex your regular expression is. And another question is, people magically use the number 3, which is trigrams. But it's interesting to see whether some other techniques can be used, maybe other different lengths, like bigrams or 4grams, or some combination of different lengths. In the past, we did one paper called a V-gram, which means you can use grams of different lengths based on the frequencies of the grams. So I think this is a place where many other algorithms can be introduced to make regex expression much more efficiently evaluated.
But some of the comparison is not exactly a fair comparison, right?
Right.
Like for example, for Mosquito question mark or marketing, you can rewrite them into dictionary.
Correct.
And then the system T operator for dictionary is much more efficient than
Yeah.
regular expression.
That's why the purpose of this comparison not to show we are faster. That's not the purpose. Just want to give you some numbers. Right?
Yeah, I think the main takeaway here is that we could apply some of the, let's say I have very complex regular expression or complex rules in system T, but we can filter the document we need to process first using some simple queries like this. Then we can speed up the overall performance because we can narrow down the set of documents very fast. Then we can do more complex processing
Correct.
afterwards.
And plus, I mean, you have a very nice proprietary automaton evaluator, right? That's not available on the market. And we did one experiment for one regex. We use a standard Java regex evaluator and use a system T's evaluator. Yours is much faster than the one available on the market. So this is something you
We
have.
have our own regex evaluator, which is much faster.
Question? Question? Okay. So I'll skip this one here because this one can be very controversial. Open problems. I already mentioned some of them. One direction is we want to add more operators. We only implement some basic operators. Some operators I would like to include. Some students are working on join operator, also influenced by the system T. How to join the inputs, the outputs of multiple operators based on the span conditions. These two spans that overlap, so they can do a join. Another example is based on the Republican National Convention speech. I cheated there because for that scenario to work, our current operator does not work. Does not help. For that operation to work, you have to be able to compare to documents. So it'd be very nice to say, I give you one document or even a set of documents, find all the similar documents, right? So you treat documents as the input. Sentiment analysis, even other very, very commonly used operations can be modeled as operators. Reg expression is something that's technically very interesting. And we see the value of regex. Let's see few studies on how to make it indexable. And we have few ideas to make them more efficient. One idea is the current algorithm ignores the position information completely. The position information means these two sub-expressions, they have to appear within a certain distance. Okay? And this when you do a translation, this information is ignored completely. But if Luxin can support this kind of a proximity search, where you can specify some conditions and positions, then we might be able to come up with one algorithm where when you generate a final Boolean expression, that expression also includes some position information that can significantly reduce the number of candidates. Because the main bottleneck is the number of candidates, and want to make it as tight as possible. And even during the translation phase, some of the decisions made by the algorithm are still up to discussion because they can be better. We have not done the language yet because we're still in this runtime design phase. But once we have the language, those issues will come out very naturally. How to do query compiling, rewriting, query optimization. Now, a new field is becoming very interesting, which is how to do text-based cost estimation and the cardinality estimation. Right? And I think I did talk about to some of you about Ragoon. And one reason that DB2 didn't take text at the first class, and one of the reasons was text is hard to deal with when you do query optimization, because it's hard to predict the cost of some of the operations in terms of the cardinality and the CPU and other resources consumption. The other thing we want to do in this space is, so far we only do one task, we get the results, and that's it. But it'd be really nice if you can also put the annotation information back to somewhere as some labels, as some metadata, possibly into Luxin or another open source package. We're looking at the Derby for now. If you can add this additional annotation information into your store, and then you can enhance your query language to specify some conditions using the additional annotations. For example, you could run something to say, run some classification algorithm about the meaning of each document. Maybe this document is about politics, that document is about entertainment, this document is about sports. If you do these annotations and store the annotation somewhere in your whole system, later you can say, and for all those sports documents, or for all documents that have already some digits inside it, I run some operations. And this additional annotation information could be utilized to make the application easier to write. You can still avoid scanning all the documents one by one. So that's not quite clear to me how the annotations can be stored separately and how to modify the language on top of the annotations. And then now, currently, with just doing information extraction, we believe text is a very rich area. There are many other things we can do beyond the information extraction. So this summary of where we are. This box is encapsulating what we have done at the library. We're still working hard in this box, and we're going to stabilize all the operators, make them more performant, and get more insights of those things. And we want to optimize. Next, we may optimize the regex expression evaluator. And once we make this one in a good shape, we'd like to jump into the query language, query compiler, optimizer phase. That's going to be future work. So I'm very proud to do this work with a team of very energetic students. It's amazing for me, it's an experiment. This is the work that for the first time I'm doing with this whole bunch of students. And so software engineering becomes very challenging because we all know students, they come and go, and how can we make sure when they go, the work can still continue. And
These are all your students?
They're all my students, but most of them are masters and PhD, masters and undergrad students.
That's a lot of students.
Yes, and this, I mean, you can see the activities on the GitHub. And each of them contributes to some of the operators. So each operator has about 2 to 3 students being worked on. And some of them still working as we speak currently. We put everything on GitHub, so you can see our dirty laundry. Any comments, I would love to get your feedback. So that concludes my talk. Thank you very much. Questions? Or more questions?
Okay. Initially, you said that one goal is for the system to be flexible when you have updates to operators, the regular expressions, and dictionaries. So you can only update a small number of operations. But I don't think I followed how you did that.
So updates, by updates, like currently, since Luxin supports updates, we have not done the operator yet, but we will, which is operator using which the user can add more documents or delete documents. So because it's more like a database system, information can be modified.
When you change a small number of documents, you can limit the operation to these updated documents. But suppose you make a change to regular expressions, how do you know that it will affect a small number of documents? I have to just rewrite it on every.
Yeah, the question is really about.
Paragraph every document.
Yeah, the question is about if we modify a regular expression, what do we do with the new regular expression? Maybe I was not very clear. The motivation of our work is previously, if you don't have such a system, if you modify your regular expression, you had to scan documents again, one by one. I think that's what he does. But if this one is successful, then if you have a new regular expression, you still need to run it again. But the difference is now we have index available for you. The index, which is already pre-built, can make the evaluation of the new regular expression much more efficient. That's the value proposition of this work.
So the index is part of the regular expression itself.
The index is part of the storage, and the new regular expression will be converted to possibly a new Boolean expression. The new Boolean query will be answered using the index structure, and the index can help you make it faster. But that's a benefit. So first, let me repeat the question. The question is, in some cases, the user can give a whole bunch of regular expressions, and then since they have so many expressions, they try to optimize the evaluation of a lot of expressions on the documents using a scan-based approach. Whether we have done this kind of a comparison? The answer is no. We haven't done anything in that space yet. I mean, our current focus is really about a very simple case where you have a document collection, you have one regex, how to make it very efficient. And so now there are 2 dimensions here, right? One dimension is you have more regular expressions. The other one is your documents can become indexable. For us, we take the second dimension, which is making the documents indexable. Now, once we do a good job in this space, the question you asked is very valid, which is if we already have index available for the document collection, and we have a whole bunch of regular expressions, how to optimize this whole bunch using those indexes? I don't have the answer to the question yet.
Database systems and visual text operations, where again, pretty much everybody would be storing their documents in some database and then doing specific operations on top of them. So there was somewhere from Columbia and then somewhere from Yahoo. So have you compared your system with those?
The question is whether we have compared our work with earlier work in 2000s storing text inside database systems, and then supporting the operations inside database systems? The answer is no. We didn't do it. And also, I'm just curious. At the end, that any of these systems become like really deployed in any application? Yeah, but I'm not criticizing anybody. I'm just saying. Personally, I believe pushing these operations inside the database system is
they're not pushing inside the database system. They are implementing their own database system for storing text documents and then doing information extraction on the text document.
Oh, they did everything from scratch.
Yeah.
Oh, and then I need to take a look at their work.
So we actually have a tutorial in 2010 in Simulon where we talk about all these systems.
Yeah, I would love to take a look at the systems and even play with the systems. I mean, one thing I could be very religious here. But one thing I care a lot about is making sure the code is reusable. So there's a very strong system aspect to it, right? The idea can be the same, but you could have different executions. So given my past experiences, I'm very rigorous about the software engineering aspect.
These people have papers published, so I think the systems are not available.
I will take a look for sure.
You can compare and see what
I will. Yeah. Thanks for the pointer. Any other questions?
Dr. Assistant support multiple language?
The question is whether we support multiple languages. The short answer is yes, because Lucene supports it. We can get a free ride.
But I think there's some tricky things here, right? When you use Lucene standard analyzer or any of the analyzers, some underlying assumptions or underlying implicit operations doing. So for example, in standard analyzer, doing stemming, doing stop words, removal, and so on. So how do you convey that to the user? Because the user may the results may look surprising to the user because it's not exactly match. Right?
I think the deeper question is what kind of a users we are targeting. I don't think that this system will be used by some user that does not have any knowledge about this space. I think we are targeting those experienced users. That's my conjecture. For people who are willing to give it a try, they should have some knowledge in the space, and they have to rely on the documentation to see the meaning of each analyzer. I think that's my view in that direction. I mean, some person without any training in this space, very likely they're not the users for the system.
Okay. So they need to understand for each of the analyzer what are the...
Yes, and we can use the standard documentation. And that's one benefit of using Lucene. Right? The one main reason, because we don't want to spend lots of time implementing different analyzers for different languages. That's just too much work, and that's not a focus of our work. So that's a trade-off we have decided. Other questions?
I think we are going to have more discussion in the afternoon. Talk about how do we.
Okay. Well, thank you very much for your attention.
Okay. Thank you.